Do you remember that iconic scene from Back to the Future Part 2, where Marty McFly hovers through the streets on a hoverboard, defying gravity as if it were something mundane? Ever since that movie hit theaters, many people have been left with a question in their heads. If we already have multifunctional smartphones and artificial intelligence, why don't we have flying skateboards, cars suspended in the air, or trains that glide without needing tracks? Has science simply gotten stuck at this point? The truth is that the answer involves much more than a lack of creativity or resources. Gravity might be the weakest of the fundamental forces, but it's stubborn like few others. We can overcome it with rockets, yes, but cancel it out? That's a completely different story. It's precisely at this point that the idea of anti-gravity enters the scene, a possibility that fascinates scientists, challenges physics, and still feeds dreams inherited from science fiction. In this video, we're going to explore whether the concept of anti-gravity is really just fiction, or if there's a scientific foundation that could, one day, lead us to levitate through cities like in the movies. Get ready. We're going to dive into real experiments, bold theories, exotic particles, and mysteries that even science hasn't managed to completely decipher yet. Spoiler? Reality is even more curious than fiction. When someone talks about anti-gravity, most people imagine objects floating in the air as if by magic. In practice, what we call levitation doesn't always have to do with canceling gravity. A good example of this is MagLev trains, which use super powerful magnetic fields to hover over tracks. The Shanghai MagLev, which connects the airport to the city center, reaches 430 kilometers per hour, suspended just a few centimeters above the ground. They don't directly defy gravity. They just balance it with another equally impressive force. This force comes from the magnets themselves. When a magnetic field strong enough repels another, it's as if the object were flying. But here we discover something fundamental. The gravitational force continues pulling with everything from below. The secret of magnetic levitation lies in the Lorentz force, which acts on charged particles in motion. In the laboratory, scientists have already managed to make small objects levitate using diamagnetism, like when they place a piece of graphite rising above neodymium magnets. However, this brings us to a fundamental distinction that defines the entire search for anti-gravity. Anti-gravity, in the pure sense of the word, would be like pressing a button and turning off the gravitational force of an object. No magnetic support, no thrust, just hovering in the air. It's an idea as powerful as it is improbable, because so far, no one has managed to prove that it's possible to neutralize gravitational force without resorting to another known force. Still, this has never stopped science from trying. Curiously, among the four fundamental forces of nature, gravity is the weakest. Compared to the electromagnetic force or the nuclear force, it seems almost timid. You can use a refrigerator magnet to overcome the gravity of a coin. This shows its apparent fragility. But try to do the same with a car, a mountain, or an entire planet. Then we discover that this weakness is completely deceptive. What makes gravity so difficult to overcome is precisely its absolute persistence. It acts anywhere, all the time, on anything that has mass. There's no off button, and no known material blocks it. The only way to face it is by using other forces, and this is where physicists' creativity comes in. Faced with this absolute persistence, scientists sought creative alternatives. One of the most investigated paths was the use of gyroscopes, devices that spin at high speed and seem to resist changing direction. There were those who believed that, if they spun in the right way, they could generate an anti-gravitational effect. All tests showed that the gyroscope can defy intuition, but it doesn't defy gravity. Between 1996 and 2002, NASA took this dream seriously and invested in a program called the Breakthrough Propulsion Physics Program. More than $1 million were applied to research on advanced propulsion, including the possibility of creating real anti-gravity. Despite the enthusiasm, the result was a chest full of reports, without a single object suspended in the air without support. The effort opened doors to new ideas and kept the debate alive in the scientific community. Today, anyone who wants to try their luck can aim for the Goethe Award, a German prize of €1 million offered by the Goethe Foundation. The proposal is clear. Make an object levitate for a full minute without using electromagnetic, aerodynamic forces, or any tricks. Just pure and verifiable anti-gravity. The prize still hasn't had winners, but the simple fact that it exists shows that science remains open to bold ideas, as long as they come with solid evidence. When we talk about mass, not everyone knows that there are two very distinct types: inertial mass and gravitational mass. The first is linked to the resistance that a body offers when being accelerated. The second has to do with how much this body is pulled by gravity. For ordinary matter, these two masses have always been equal, at least as far as we can measure with precision. This balance gave rise to the equivalence principle, one of the central ideas of general relativity. It was based on this that Einstein realized something brilliant: the sensation of being still in a gravitational field and that of accelerating in a rocket can be exactly the same. This view changes everything, because it shows that gravity isn't just a force, but a direct consequence of space-time curvature. And it's precisely in this context that a fascinating question arises. Antimatter enters the game. Shrouded in mystery, antimatter has always had a special air. In fact, if you want to delve deeper into this subject, we have a specific video about antimatter and the CERN experiment. Now, speaking in simplified terms, it's like the inverted reflection of ordinary matter. Antiprotons, positrons, antihydrogen atoms. When we talk about gravity, the big question arises: does antimatter also get pulled downward? Or does it behave differently, perhaps even hovering in the air? If there were levitation, it would be a clear sign that antimatter has negative gravitational mass. In this case, we would be facing a possible path to understand or even master some type of antigravity. More recently, the gravitational behavior of antihydrogen at rest experiment is being developed specifically to test how antimatter behaves under the influence of gravity. Each experiment brings us a little closer to the definitive answer. Antimatter seems to fall like anything else, but the technical challenge is immense since these particles are extremely unstable. Even so, each attempt teaches us something new about how gravity works at the most fundamental level of reality. But while we search for these fundamental answers, it's worth imagining, what if anti-gravity were discovered tomorrow? The implications would be revolutionary. Imagine transportation systems that don't depend on fuel, cars, trains, and airplanes that simply turn off gravity to move. Space exploration would be transformed. We wouldn't need giant rockets anymore to escape Earth's attraction. A simple spacecraft could rise from the surface to orbit with minimal energy expenditure. Civil construction would be reinvented. Skyscrapers would no longer have height limits, since weight wouldn't be a problem anymore. We could build floating cities, solve urban space problems, and even create sustainable orbital habitats. In medicine, anti-gravity could revolutionize treatments for people with reduced mobility and open new paths for therapies in microgravity environments. The global economy itself would be transformed. The transport of heavy cargo would become trivial, completely changing world logistics. Entire sectors of industry, from aerospace to construction, would need to be rethought. It would be a revolution comparable to the invention of the steam engine or electricity. Currently, laboratories around the world continue investigating phenomena that could bring us closer to understanding anti-gravity. The Massachusetts Institute of Technology has researched materials with unusual gravitational properties. At the University of Tampere in Finland, scientists study rotating superconductors that seem to produce anomalous gravitational effects, although still controversial. In China, researchers from Shanghai Jiaotong University investigate how ultra-intense electromagnetic fields can affect local perception of gravity. Although these studies are still in initial stages, they represent serious attempts to find loopholes in the laws of physics we know. In the territory of scientific dreams, the idea of anti-gravity still lives. Just like time travel and perpetual motion machines, it fascinates us because it seems to promise a leap beyond the possible. What we have so far are clues, hypotheses, and experiments that bring us closer and closer to an answer. And perhaps this journey of discovery is precisely what makes science so fascinating. Despite being so everyday, gravity still holds deep mysteries. Just think about black holes, where space-time bends to the limits of comprehension. Or Lagrange points, regions of space where the gravitational force of two bodies balances perfectly. These are real and proven phenomena that show how much we still have to learn about this force that shapes galaxies and sustains our own bodies. For now, anti-gravity continues to be a concept that challenges our current physics. Who said that's a problem? Today's impossible can be tomorrow's technology. And when we look at everything that has already been discovered, we realize that understanding is just the first step, because knowledge is just the beginning.